In this video, we're going to learn about exceptions to the periodic trends. So, if we look at the periodic trend of ionization energy, we're expecting high ionization energies to be further to the right and up. And if you look at a comparison between lithium and nitrogen, you can see further to the right, we have a higher ionization energy. But what's really weird is that as we go across, we see lithium, okay, it's higher for beryllium, but then it actually drops down for boron before continuing up with carbon. And the same thing is also observable in period 3 as we go from magnesium to aluminum. There's a drop that you otherwise wouldn't expect. So we can explain this through our understanding of the energy of electrons in different subshells. So for beryllium, we're going to have a 1s and a 2s, and that should be 2s. 2s, there we go. Okay, 1s has 2 electrons in it. The 2s also has 2 electrons in it. But for boron, we have 1s, 2s, and 2p. I'm actually going to draw the 1s slightly lower, since it's true that boron does have one more proton in its nucleus, and that actually will make the 1s a little bit lower in energy because the electrons are being held a little bit more tightly by that nuclear charge with one more proton for boron than for beryllium. But thing is, boron also has the 2p that has an electron in it. And the important thing to understand here is, ionization energy is the energy required to remove an electron, which means just whatever electron has the highest energy. So in the case of boron, we're removing a 2p electron, and in the case of beryllium, we're removing a 2s electron. It's easier to remove the 2p electron from boron than it is the 2s from beryllium. How do we know this? Well, because the ionization energy of boron is lower. And yeah, we're talking about two competing factors. Yes, boron has one more proton than beryllium, which should make it have a higher ionization energy. But on the other hand, the 2p is easier to remove than the 2s. And just which of these two factors wins? Well, apparently the fact that boron's electron is in the 2p, and that's higher in energy than the 2s of beryllium, that's the factor that matters most. We know this because the periodic trend is broken. We can see the measurable data. And you can make a similar argument for magnesium versus aluminum in the sense that we're talking about a 3p for aluminum that's being removed and a 3s for magnesium. But if we go down the group, we can find that you don't get the same trend continually as you go further down the group. So for example, boron, right, it has a lower ionization than beryllium, and aluminum has a lower ionization energy than magnesium, but gallium, well, it has a lower ionization energy than calcium, but they're very, very close. Notice, the difference between beryllium and boron is 99, it's almost 100 kilojoules per mole. For aluminum and magnesium, it's 160. But by the time you get down to gallium versus calcium, the difference here of 578.8 versus 589.8, that's only 11 kilojoules per mole. And actually, when we go to indium versus strontium, you find that indium actually has a higher ionization energy than strontium. And the reason that we get this change as we go down is that as we go down the periodic table, we get more stuff in between groups 2 and group 3. We get the D block. And so notice the number of protons in the nucleus. Well, before it didn't seem to matter. Oh, we get one more proton for boron, but its 2p electron is still going to be higher in energy than beryllium's 2s. Well, what if we get 11 protons in the nucleus that are differentiating between our gallium and our calcium? What if we get 25 protons in the nucleus that are really, really pulling down the energy level of, say, thallium's outermost p electron. Those 25 protons are really, really pulling in the outermost electron for the thallium, the p electron. And so actually that p electron is going to be lower in energy than barium's s. And as a result, it's going to be harder to remove the electron from the thallium than the barium, just like it's harder to remove the outermost electron, the p electron from the indium, than it is the s electron from the strontium. Again, you should just be looking at the fact that the periodic table broadens as you go down. And in the case of going from calcium to gallium, now we've got the whole D block to fill. A lot more protons in between calcium and gallium. Same with strontium versus indium. And when we get down to barium, we're not just considering adding in the D block, we're also adding in the F block. And that's how we get a proton difference of 25. So we should also consider another exception to ionization energy, which is, again, we're expecting an increase in ionization energy as we go to the right, but we see that oxygen has a lower ionization energy than nitrogen. So we get up, 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 down, up, up. So why is this? Again, we have to look at the energy of electrons in the atom. And for, we're going to have a 1s, we're going to have a 2s, and we're going to have a 2p. Now, the 1s is filled with 2 electrons, the 2s is filled with 2 electrons, and for nitrogen, we use Hund's rule and make it so that we have 1 electron in each of the 2p orbitals, rather than pairing up any. And we know this because electrons repel each other, so why should you put 2 electrons in the same atomic orbital when you can put them all in different orbitals so that they have their own space, they're separated from each other? Similarly, why would you sit next to somebody that you don't know on the bus when there's a perfectly empty space across from them? So that's the configuration for nitrogen. But when we go to oxygen, we're adding 1 more, and now we have paired these 2 electrons. And now there's a little bit extra repulsion. Yes, there's 1 more proton in the nucleus for oxygen, but that still does not counteract the fact that there's a lot more repulsion going on here, and that makes it easier to remove an electron from oxygen. And similarly, we can find that the atomic radius of oxygen is greater than that of nitrogen. That has to do, like you can see, the radius is bigger. That has to do with the fact that there's now pairing and there's now more repulsion between electrons, and that does cause them to spread out a little bit more in the case of oxygen relative to in the case of nitrogen. Nitrogen, we have the 2p with 3 electrons, and there's less repulsion here than in oxygen, where we have pairing in 1. And actually, you can see that even fluorine is going to have a bigger radius than nitrogen, because in spite of the fact that there are now 2 protons more in the nucleus of fluorine than in the nitrogen, you should be thinking that those 2 extra protons are pulling in the valence electrons a little bit more, we still have more electron repulsion in the outermost shell. You have to get up to there being 3 more protons in the nucleus of neon to get to the point that we're back to the same atomic radius, 70, as we have with nitrogen, 70 picometers. In the case of neon, same radius as nitrogen, obviously a lot more electron repulsion in the p orbitals, right? But the 3 extra protons counteracts that, and now it's pretty much equal. It's a wash between those 2 competing factors. So these have been some exceptions to the periodic trends that are explained by electron configuration and the different energies of orbitals and the different amounts of electron pair repulsion. Ultimately, everything comes down to attraction between protons and electrons. It's just how you explain it and what you're considering. So I hope this video has been helpful. Please let me know if you have any feedback in the comments section. Also, if you have any questions. Thank you.